Welcome to Xcoder Videos and to what I think is the fourth in our series of videos on the Microhard program. In today's video, we're going to be looking at the tasks, or a couple of the tasks that we unlocked in the last video. In our last video, we unlocked the multiplexer, the demultiplexer, and the half adder. And today we're going to look at the multiplexer and the demultiplexer, and we're going to save the half adder for a video of its own because we're getting into binary arithmetic there, and that's a good place for us to introduce binary notation. And I think everyone knows if you're playing this program, you probably have some understanding of binary representation. And we're just going to discuss it briefly in the next video, and then use that as an introduction to the half adder. But for today's lesson, we're going to be looking at first the multiplexer, or the MUX, and then we'll look at the demultiplexer, the DEMUX, which is, I guess, kind of the opposite of a multiplexer. So let's go ahead and take a look at the multiplexer specification. In the specification, the description of the multiplexer is the MUX element has two data inputs and one select input and one data output. If the select input is 0, the data from the first input is transferred to the output, and otherwise the data from the second input is transferred to the output. You can kind of see that in the graphical representation down about halfway down the screen. Two inputs, N1, N2, a select input, and then the output. And the idea is, depending upon the value of the select input, we're either going to put the value of N1 on the output or the value of N2 on the output. The truth table then for the multiplexer is shown down below. It shows 3 different inputs. That means we're going to have 8 combinations of the way that 8 different ways the inputs can be configured, and then the outputs for those. If you'll notice, under select, the first four values are 0, and the last 4 values are 1. When select is 1, you'll notice that the out value is equal to the first 4 values of the N1 pin. And if select is 1, then you'll notice that the out value is equal to the last 4 values of the N2 pin. And that's what we mean by selecting. We mean we're getting those data values from the inputs, either N1 or N2, to the output. Let me give you a picture of how I first thought to configure the multiplexer. And my first attempt at configuring the multiplexer here in the digital program that I'm using was a bad design, and I'll show you why in just a moment. But look at the logic. We basically have 2 AND gates, and each one of these AND gates can be thought of as a selector, an individual selector. And notice that we have N1 tied to one of the pins and N2 tied to the corresponding pin of the AND 2 gate. And you can think of this gate as you can think of this AND gate as a door. And if the door is open, then the N1 value is allowed to go through. And if the door is closed, the N1 value has no impact upon the output. And the same thing is true of the other gate. The N2 is kind of like a door. If it's open, the N2 value gets out to the output. And if it's closed, then the N2 value has no impact on the output. And the second pin of the AND gate determines whether the door is open. If the pin is high, if the input to the AND gate, the second pin of the AND gate is high, then the door is open. And if the the second pin of the input is low, then the door is closed. And so in the case of the second AND gate, if the the select input is high, then the AND 2 gate will be open. And we can use the same value to tell the AND 1 gate either to open or close, but we have to take the opposite value of the select in order to control the AND 1 gate. And you get the opposite value from an input by using the NOT operator. And so that's what we have right here. We have the NOT operator. So when select is low, the NOT operator turns it into a high value and opens the door. And it turns out that in this case, if this were to work, if this is 1, then that would be 1. If this is 1, that would be 1. And only one of these would be 1 at either one time, because only one of the doors can be open. If this value is if the value is not 1, or if the door is not closed, or if the door is closed, pardon me, then the output value of the AND gates would be false or 0. Well, what was wrong with this? I'll show you how I found out it was wrong by running the simulation. And if we first look at the simulation, we see all 3 input values are off, and that means that the AND 1 gate is open and the N1 is off, so that gets through the door and it goes to the output and everything is as you would expect it to be. If we turned on N2, N2 is closed because it has a low value here on the second pin, and so it doesn't give any output, so we have the output there. If we turned on the select button here, we get an error. Error calculating step. More than one output is active on a wire, causing short circuit. And this is saying we have an output of 0 in the first AND gate, an output of 1 on the second AND gate. And when you put a 1 and a 0 together, it's saying, well, you can't do that. Which of the selections, which of these two values are going to go to the output pin? And so it flags that as an error. I'll say this in my own defense. One of the ways to create, basically what let's see, how do I want to explain this? If this wire was grounded with a high impedance resistor, then the circuit here would basically work, because even though one of the values is at 0, assuming that value is at ground, putting a high voltage value on the wire would not hurt anything, because you have a high impedance there, and it would just generate a voltage across that impedance with the high value, and the output would get out. But the way this is designed, it's flagged as an error. Let me load up my second solution to the multiplexer and see what the difference is. All right, the only difference is I've added this OR gate now. Now it doesn't matter if one of these is 0 and one is 1. The OR gate, if either one of them is 1, then the OR gate will let it out. And because of the truth value of the OR gate, that is exactly what we had in mind. As a matter of fact, one of the ways, and let me just put these up together so we can compare them for a moment. One of the ways to create an OR gate is what I've done right here. Is just tie two wires together. Of course, you do need to have, usually would have to have some kind of high impedance resistor from this part of the design to ground, so that that allows you to pull that value high if one of the AND gates has a high output. And so that's one way that an OR gate is made. So it's not that much different, but because of the logical way the program's working, this was flagged as an error. That's okay. This will definitely work, and it's probably a better design. A little bit slower because you have electronic circuits going on in the OR gate. That slows it down a little bit, whereas just a direct wire like I had it would be a little bit faster than the integrated circuit would be. But the multiplexer, this multiplexer works just right. Here's the truth table for it. You'll notice the truth table that I have here, that I've written out, is the same as the truth table down here. The select input N1, N2, and all the outputs are as they ought to be. So this is the way we'll design our multiplex. Let's go into the Microhard program and get to working on the design. We have 3 inputs, N, 1, N2, and select. We have 1 output. And for the parts, we'll need let's see, we'll need 2 AND gates. We'll have and 1 is an AND gate, and 2 AND gate, and we need an exclusive OR. Just one of those is enough, and hit the wrong key there. And we need a NOT gate. And I believe that's all the components that we need. Let's go in now and wire this up. Wired up, we'll start with the N1 and N2. N1 to and 1 dot N1, N2 that's going to go to and 2 dot N1. Then we need to wire up the select to not dot in, and the select, notice this select has two outputs. It's okay to tie outputs to different inputs, and the select is going to go to and 2 dot N2, and then the not dot out will go to and 1 dot N2, and the last thing we need, well, it's not the last thing, but now we need to tie the output for the AND gates to the OR gate. The exclusive OR gate. No, it's OR gate. And why do I have an exclusive OR there? So that is wrong. Let's go back up and fix that. Guess I was thinking of something else. OR dot N1 and 2 dot out to OR dot N2, and finally OR dot out. Tie that to out, and that should complete our design. And that is the wiring diagram, or the wiring specification for, or the wiring design, I should say, for the multiplexer, the good multiplexer that I showed just a moment. So let's press Control Enter and see if we got that right. Verification failed. Let's see what happened. Following errors were found in the design. Wire not out. Wrong syntax for one of our lines. So let's go back and see. Forgot. I missed the arrow greater than symbol. That should work now. Let's find out. There we go. And it passed. And so now we have completed the MUX design. And now I've unlocked a new task, which is the MUX 4B, and we'll have to come back and work that. Maybe we'll just do that with the half adder later on. That may be a good way to fill that out. So let's go ahead and click OK. And our next design that we want to create is the DEMUX specification, and it is already highlighted here. So let's take a look at the description. The DEMUX element has one data input and one select input and two data outputs. If the select input is 0, then the data is transferred to the first output. Otherwise, the data is transferred to the second input. So select is 1. Then the second output is the data that we're interested in. If it's 0, then the first output is the data. The value of the output not taking the data bit value is always 0. So out 1 and out 2 are always 0, except when n is 1, and then the output 1 or output 2 is 1, or output 2 is 1, depending upon the value of the select input. The truth table down there shows that when select input is 0, then the output will be, the output 1 is going to be equal to the input. When the select input is 1, then output 2 is going to be equal to the input. Otherwise, those values are going to be 0. All right, let's take a look at a design for that. Pardon me. We'll come up here and open up the DEMUX design. There we go. The DEMUX is an output selector, just another way of describing what the DEMUX does. It has two values, two input values, in and select, and two output values, out 1, out 2. When cell is 0, data is transferred from in to out 1, but when cell is 1, data is transferred from in to out 2. And otherwise, out 1, out 2 will always be 0. Well, to do that, we're going to use AND gates again to select the output. The input is sent to both AND gates, but the selector is tied to both AND gates with the NOT operator on the select input for AND 1. And there's some similarities between the demultiplexer and the DEMUX, and the multiplexer. We've just moved some of the inputs around a little bit to get a little bit different benefit out of this component. So let's go ahead and put this into the Microhard. Specify our parts. And the parts are, we need 2 AND gates, and 1, and 2, and we need a NOT operator. In this case, we don't need the OR gate because we have 2 outputs. So let's now go in and wire this up. We'll have N is going to be tied to AND 1 dot N1. N is also tied to AND 2 dot N1. And cell is going to be tied to the NOT operator. The NOT operator is going to be tied to AND 1 dot N2, and cell is going to be tied to AND 2 dot N2. That leaves the AND gates and1.out is tied to out1. And 2.out is tied to out2. And that should complete our specification. Let's take a look again at our diagram here, and we've got the N1 to and1 N1. We also have the N to and2 N1. We've got the select to the not in. We've got the not out to the second input to and1. And we've got the select to the second input of out of end and 2. And then out1 out is tied to out1, and out2 out is tied to out2. So that should work. Let's hit Control Enter and run our test. And the verification passed. And we click OK. And we now get a new task, DEMUX 4W. So the MUX 4B is a MUX that uses a 4-bit bus, and DEMUX 4W is a DEMUX that has 4 outputs. And so those are going to be interesting. Well, that is all that we had planned for this particular video. We appreciate your coming. And if you like the video, all that we ask is that you just give us a thumbs up. Let your friends know about this if they are interested in this program. Also, we've mentioned before, if you're a member of Steam, look us up on Steam as Xcoder. My first name is Gil, and give us a shout. Thanks again for watching. We'll see you again next time.